In a ball or rod mill, the weight of the load inside the mill is mostly grinding media, around 82% steel and 18% slurry. In overflow mills, this ratio is relatively constant, so the power is more or less constant unless there is a shift in the center of gravity of the load, for example, due to a change in viscosity. In sag mills, the proportion are about 52% steel, 20% coarse ore, 26% fine ore, and 2% water based on a ball charge of 8% and of a total charge of 30% of the mill volume. Since the great discharge holds back coarse particles, the total charge will vary depending on grinding conditions. The changes in mass and particle size distribution in the mill will affect the weight and the center of gravity of the load and therefore will affect power. This can be summarized in this power versus load relationship for AG and SAG mills. As the load is increased, power increases due to the increased weight until a peak is reached. After the peak, power is reduced because the center of gravity of the charge moves towards the center line at a rate faster than the increase in weight. Coarse particles are rigid bodies that can be keyed by the lifters and therefore lifted high. Fine particles, on the other hand, behave as part of the slurry and flow off the lifter, resulting in a lower lift. For a fine mill load, the contribution of cataracting is reduced. Since, for a given mass, cataracting contributes more to power consumption than cascading due to its center of gravity being further away from the center line, the net effect is a reduced power consumption. If the mill power is controlled, then the set point for a finer mill load should be reduced. As the figure shows, the power set point for the coarser mill load cannot be reached when a fine mill load is present. Attempting to do so would only lead to an overload, as tonnage would keep increasing in an attempt to reach the power set point. If the mill load particle size changes, there is a shift from one curve to the next. In this example, the feed tonnage is reduced at point B. Depending on mill conditions, especially pulp lifter pumping capacity, it is possible that the mill load becomes coarser due to the decrease of fines in the mill. In this case, the power-load relationship moves to the upper curve. Note the increase in power. In some situations, it's possible to exceed power constraints. If tonnage is increased at point D, then the power load may shift back to the lower curve by the increase of fines in the mill load. Notice that from D to A, load is increasing and power is decreasing, normally a sign of overload. Knowledge of the load range where the peaks occur will help determine if a curve change occurred or if an overload is in progress. When the ball charge is increased, the power is increased, since they have the same effect as more coarse particles, more cataracting. Also, since steel balls have a higher density than ore for the same volume in the mill, the load will be heavier. The peak shifts to the left as ball load increases because the effect of increasing mill load on the toe of the load, supplying power, is enhanced at higher ball loads.